Okay, cool. Okay. Hey, everybody. I'm Andy. I'm going to talk to you about Scikit-learn and advanced features in Scikit-learn. So in this first NLP meetup, I'll mostly be talking about ML and very little about NLP. But I got invited, so whatever. So about myself, I did my PhD at the University of Bonn in Germany, working on computer vision and machine learning. And I went to Amazon Machine Learning, their office in Berlin. And now I'm working at NYU Center for Data Science, where I work as a research engineer, where contributing to Scikit-learn most of my time. So I want to get like a quick idea of what the background of the people in the room is, because that really depends on how fast I'm going to go through the different parts. So who here has used Scikit-learn before? Okay, nearly everybody. Good. Who here has used a grid search before? Woo. Okay. Who has used the bag of work module? Okay. Cool. Then I'm going to explain everything that I was going to explain. So a little bit of background on Scikit-learn. As you may know, it's a Python library to do machine learning. It's a pretty big like open source community around it. These are, I think, the 36 or something core contributors. Together with Olivier Grisel, I do the releases. I joined the project like 5 or 6 years ago, I think. And yeah, it has algorithms for most of the standard machine learning or implementations of most of the standard machine learning algorithms, and a lot of stuff for feature extraction, preprocessing, and so on. All of Scikit-learn assumes that we represent our data as a 2D array or matrix, where each row corresponds to one sample, and each column corresponds to one feature. So one sample is one data point, one thing I want to reason about. One feature is a property like age of a customer, or I don't know, whatever. So that's sort of the standard data format. And Scikit-learn also assumes that all properties are continuous, more or less. And often we want to do supervised learning, want to predict the target, and we assume the target is like a one-dimensional vector that is either continuous for regression or categorical for classification. And so this is sort of the basic data representation, and I keep calling the data X, capital X, and the data lowercase y. So because most of you already used Scikit-learn, only a very brief outline of the API. So all of the algorithms and basically all the functionality is implemented in Python classes that we call estimators. All of these classes have a fit method. And the fit method always takes the data X. And if it's a supervised algorithm, it also takes the desired output Y. So this is to build a classifier, for example. Then, depending on what the model is, the model has either a predict or a transform method. Predict means we want to predict a label or some output that is either continuous or discrete, but usually 1D. So that's the case for classification, regression, or clustering. So model.predict gets the data X and will make a prediction for the data. If you want to use the data and create a new representation of the data, you need to use the transform method. That's for scaling the data, for dimensionality reduction, for manifold learning, feature extraction, and so on. If you want to do a PCA for on your data, and you need to use the transform method. So these are the 3 most important methods in Scikit-learn. All models have a fit method and either a predict or a transform method. Some have both. So before I go a little bit more into the API and about the different tools that are available, I want to talk about like one big topic in machine learning that hopefully all of you are sort of aware of, which is model selection and model complexity. So all of the models have some parameters, and we usually need to tune the parameters to get good performance. So we're always looking for building a model on a training set, and we want the model to be accurate on new unseen test data. And this is usually controlled using some knobs. And these knobs that can be regularization parameters or a number of layers in a neural network, I call them model complexity. So this is basically all models have some way to control model complexity. And here, this chart shows model complexity against accuracy here on the training data. So if you have a very, very simple model, like maybe linear regression, usually the accuracy is not very good. But if you use a more and more complex model, it can be the same type of model, maybe with less regularization, maybe you grow a tree deeper, or maybe you use less regularization on your logistic regression, your model becomes better and better. And at some point, usually it becomes even perfect. However, when you look at new data that the model hasn't seen yet, well, if the model is too simple, you'll also have very bad performance. But as your model gets more and more complex, you will get better. But at some point, your model becomes too complex, and your generalization performance suffers. At this point, you're basically memorizing the noise that is in the data. And this is what's called overfitting. So if your model is too simple, people call this underfitting. If the model is too complex, it's called overfitting. You usually want to find some sweet spot in the middle. And a lot of the tuning in machine learning is about how can I pick a model that is powerful enough but not too powerful. And so I want to talk about some of the tools we have in Scikit-learn that can help you with this. So the first one is cross-validation, which allows you to evaluate a model. So what cross-validation does, you provide a model and some data, and it provides you a robust estimate of how well the model does on this data. I guess most of you will probably be familiar with cross-validation, so I'm not going to go into details too much. You split your data up into a certain number of folds, let's say 5. You train on you train on 4 and test on the other, repeat this 5 times. This gives you 5 accuracy values. So this is much more robust than just training one model and testing on some holdout set. So you have 5 models, 5 holdout sets. You get 5 accuracy values, and you can average them or something. So this is sort of the standard case. In Scikit-learn, you can also modify how you split your data. So by default, it uses for regression at least, it uses the first fifth of the data, the second fifth of the data, third fifth of the data, and so on. For classification, what it does by default is it does stratified cross-validation. So it tries to ensure that the overall class distribution is reflected in each fold. So if I have a 90-10 imbalance in my overall data set, each fold will have a 90-10 class imbalance. So these are the defaults. But you can also change the cross-validation methods. So CV can either be an integer that gives you that many k-fold cross-validation, or it can be a cross-validation iterator, which are these classes like the shuffle split here. And these classes are some different ways to do cross-validation. Shuffle split, for example, just shuffles the data, splits it randomly, and you can control how much of the data will be in a test set, how much will be in a training set, and how many repetitions you would want to do. This, for example, allows to do very many repetitions, or it allows you to do only one repetition and do a single split, or if you want to subsample your data, use 50% for testing, but only 10% for training, you can do it with this. Another one that's kind of important is label k-fold, which allows you to do cross-validation that respects some grouping in your data. So often you have data coming from particular sources. Say you're in a hospital and you have different patients. For each patient, you have multiple measurements. So each patient has multiple data points. And you want to know how well does your model work on a new patient. If you now just do standard cross-validation, this will give you an overly optimistic estimate. The problem is that the same patient will be represented both in a training set and in a test set. And it will be much easier for the model to learn about this patient because he's both in a training and a test set. Label k-fold can be used together with some labels which say which patient does this data point belong to, and it will leave each patient either completely in a training set or completely in a test set. So doing cross-validation in this case is exactly the same as observing a new patient. And this is also, I mean, this does not only apply to health, that's also the same with hotel recommendations or websites and ads. You often have this phenomenon that your data points are grouped and you want to preserve the groups when doing cross-validation. So cross-validation is a way to basically do something better than just splitting your data in a training and test set. But cross-validation just evaluates how well your data does, how well your model does on a particular data set with a particular parameter set. Usually we don't know which parameter set to pick, so we need to adjust the parameters. The standard way to do this is grid search. So what grid search does is usually it uses internal cross-validation, and for each fault in the cross-validation, it tries out all of the parameter settings. Grid search is basically a brute force search over all possible parameter settings that you're interested in. You run cross-validation on all of these parameter sets, and you get a best model out. Or better, you get out a best parameter setting. Then you can retrain your model using this parameter setting on the whole training set. In the figure I showed here, so before I ran my cross-validation and grid search, I split the data into training and a test part. I do the grid search on the training part, find the best parameters, retrain the model on the best parameters, and then I evaluate how well does this model do on a separate test set. It's important to have a separate test set to evaluate your model, because if you try too many parameters on using cross-validation, you might overfit your parameters. You might have seen this at Kaggle competitions where you overfit the leaderboard. Someone keeps resubmitting and resubmitting some solution, and they get better and better, but on the private leaderboard, they're very bad because they are overfitting this particular validation set. The same can happen if you do just cross-validation without an additional whole load test set. So yeah, so this looks kind of a little bit complicated, I think, but it's very easy to implement. In Scikit-learn, there's this class called Grid Search CV. Grid Search CV implements grid search with cross-validation. And so this code implements everything that I just explained. So train test split at the top splits off some portion of the data as a separate test set. And then I want to run grid search on the training set. To run the grid search, I need to define the parameter settings that I want to search over. Here I use like a kernel SVM that has two important parameters, C and gamma, and I specify some ranges that I want to search. What grid search will do is it tries out all possible combinations of these two parameters. So then I construct a grid search object, and I give it the model I want to evaluate, or for which I want to adjust the parameters. Here it's a kernel support vector machine, and I give it the grid of parameters that I want to try. Now, this grid search object looks exactly like any other classifier. You can see here it has this fit and predict method that all of the models also have. But here, if I call the fit method, what it will do, it'll run the whole process of doing cross-validation with grid search. So it'll try out all the parameter settings, do cross-validation for each of the parameter settings, select the best parameter setting, and retrains the model on the whole training set. And all of this happens in this one line that's grid.fit. So that's kind of handy. Then you can use this best model that was found to predict on your test data set or evaluate with the score method. So score method just computes the accuracy of the model on the test set. So this is sort of the standard workflow that I use, or that's sort of, I'd say that's best practice. Oh, it's sort of clear what happens here? Yes? All right. Questions? Maybe I've been going a little bit fast. It's a bit hard to say. Yeah? Oh, it's brute force. So it tries out all the parameter settings. That's the standard. The problem with greedy stuff is that the objective might be non-convex. I think either now or in 5 minutes, I'm going to give you some better options. But this is sort of that's kind of the gold standard, actually, even though it's a bit stupid. So the question was, first, for recording, doesn't this become intractable for any non-trivial parameter set? Yes. So you can't do this with 5 parameters at once, but most models don't have that many parameters. Neural networks have a lot of parameters. That's why people do different things for neural networks. But most other models, I mean, these are the hyperparameters of the model, right? This is like how much regularization you want in your model. Usually you have like 1 or 2 parameters that are really important for each of the models. Yeah, it usually actually works quite well. You can, so this can be, this is embarrassingly parallel, so you can parallelize it over multiple cores. So the multiple core thing is in Scikit-learn. There are some extensions that you can do it over network if you want. But it's, I mean, this is number of folds in a, so instead of building one model, you build number of folds in the cross-validation times number of parameter settings, which is here now 150 times or something, building one model. So, yeah. Yeah, so that's what I mean. You can use different machines, but it's not built into Scikit-learn because Scikit-learn doesn't want to do cluster management. There's a thing called Spark sklearn. If you have a Spark cluster, you can just run this and it will use the cluster. You can also just buy a machine on Amazon that costs $5 now and has 20 cores and then run it on that. That's much easier. Sorry. Yeah. Yes. That's the Spark Scikit-learn is just a thin wrapper on Scikit-learn. It uses Spark just to spawn the jobs over the cluster. Yeah. So the models are thrown away that are built because we found it's too memory intensive. I mean, at the end, after the search is through, you build one model that is the best parameter settings built on the whole training set, and that is stored and accessible. And if you want to inspect it, it's like grid.best best estimator. But all the others are immediately thrown away. It also needs to, so there's a thing at the end, but it also needs to implement set params and get params, or you need to inherit from base estimator in Scikit-learn. If you inherit from base estimator, you only need to implement fit and predict, and then you're good. That's one of, so this class and the cross-validation class and the pipeline class I'm going to mention a bit. These are like the main reasons why you might want to implement something yourself with the same API as Scikit-learn, because then you can use this tooling that we have. All right, so let me go on. So I want to do a quick example application, which is sentiment analysis, because this is an NLP meetup. So this is like a very simple toy data set. It's IMDB movie review data. So some researcher went in and classified everything with 3 or 4 stars as positive, as a positive review, and everything with 1 or 2 stars as a negative review, and collected 12,500 positives, 12,500 negatives. And here's an example. One of the worst movies I've ever rented. Story had one of my favorite actors on it, Travolta, in a nonsense role, and so on. And the negative label. All right, and so we want to learn now a model that can tell us, is the movie review positive or negative? So as said before, in Scikit-learn, everything is represented as an array of floating point numbers. This review really does not look like an array of floating point numbers at all. It's a string. Each review will have different length, different number of words, and so on. So we need to bring it into some format that we can do machine learning on. The most standard format is the back-of-word representation, which I'm going to very briefly explain. It's implemented in the class countVectorizer in Scikit-learn. The basic idea is you take a string, like the review. Here I used a shorter string. You break it up into words or tokens. Here, what we do in Scikit-learn is basically just split by white space and by periods. You also have, you can normalize words if you like. Here we made everything lowercase. You could also do something like get the base form of a verb or something. So now we have a list of tokens or words. Then what we do is we build the vocabulary of all the words that appear in our whole collection of documents. So now we go over all the documents, over all the reviews from IMDb that we have, 25,000 something, and extract all the words. Now we have a very large vocabulary, probably hundreds of thousands of words. And now we can go back to each of the reviews, and we can encode them by counting how often does each of the words in our vocabulary appear. Most of the words appear 0 times, but there's exactly 6 words that appear once. So ants appears once, gets appears once, how appears once, is appears once, and so on. So we have a very large vector that's like 100,000 entries long or something. Most of them are 0, and some of them are 1. If the same word would appear multiple times, it would have a 2 or 3 or whatever. Is that clear? Who saw this before? Okay. Okay, so now we have a mechanism to get from our reviews to some very large vector. Oh, so an important trick here is because there are so many zeros, we don't store the zeros. We use a sparse matrix encoding that only remembers where there are non-zero entries. Otherwise, our hard disk or our RAM would blow up. So we can do a little bit better than this because this is called bag of words because it completely gets rid of the order of the words. So it's just like we take all the words and we throw them in a big bag and we don't care where they were in relation to each other. Whoever often thinks the relation of words really matters a lot, like if there's a not in front of a word, that means quite a different thing. So one very cheap way to get back some of the order of the words is to use what is called n-grams. N-grams means we don't only split up and look at each single word, but we also look at pairs of neighboring words. So unigrams means 1 grams, means we look at 1 token at a time. Bigrams means we look at pairs of 2 tokens that are next to each other. So the top one is extracting unigrams here. The bottom one is extracting the bigrams. So these are all pairs of neighboring words. You could also do this with trigrams and 4grams, I guess, is the next one. Usually most useful ones are bigrams and unigrams. So you usually use both of them together. And so I want to quickly show how to do this with Scikit-learn. All right. Who here has used the IPython notebook, Jupyter notebook? The rest of you should start using a Jupyter notebook. All right. So, yeah. Yeah. Go to try.jupyter.org. That's a very good idea. You should just install it. So I'm loading the text data here first. Scikit-learn has like a function that is called load files that loads text files from directory. It's not very exciting. And now we have text train is a list of strings, and white train is a list of zeros and ones. And there's 25,000 training data points, and bin count counts number of ones and zeros. And so, okay, there's as many positive as negative. Now I'll do the same thing for a test data set and look at how many, there's the same number of samples in a test data set, also balanced. There's an example of from the training set. Words can't describe how bad this movie is, and so on. Label 0, 0 means negative emotion. There, you can see there's some Unicode in here, but this will actually be fine. So I don't worry about it so much now. To build this bag of work model, we use the count vector as a class, as I mentioned before. And we just call the fit function or fit method on the training data set. This will build the vocabulary. We can see, okay, we got a vocabulary of about 75,000 words. Here, with the getFeatureNames function, I can look at what these words actually are. The words correspond to features in the feature vector. You can see the first ones are all numbers. They're not super interesting, mostly zeros because it's the very beginning. But if I go somewhere in the middle, I have a lot of words that start with pin. To get the data into the bag of word representation, I use the transform method because that's how you get new representations. And the output here I call xtrain. This is my matrix representation of the data. And you can see it's a 25,000 times 75,000 sparse matrix. So one row per text and one column for each of the words in the vocabulary. And so if we want, you can see here I chose one particular short review. They want to know, is this a positive or negative review? I don't know. It's a negative review. All right. So you can see that if you want, for each of the words in this review, there's exactly one non-zero entry in this large sparse matrix. I can do the same with the test data. Now, xtest is, again, the sparse matrix representation using the bag of words. And once I've done that, I can use standard Scikit-learn, call fit and predict. So here I use a linear support vector machine, linear SVC, give it the training data and the training labels. Here I call score on a training set. Okay, on a training set, we are basically perfect. And on a test set, we are like 84% accurate. Okay, not too bad. If we want, we can also look at the coefficients. So here I defined a function to look at the, I zoomed in too much. Can look at the most important coefficients. So it's a linear model, so one coefficient for each of the words in the vocabulary. And so here, the red ones are the largest negative coefficients. So these are indicative of bad reviews like disappointment, worst, waste, poorly, unfunny. And then here on the right, are words that are indicative of positive reviews like scary, refreshing, reeling, appreciative, and so on. But if you look closely, there are some sort of unexpected words like hairy and squirrel and Australia and Angelina. I don't know. They shouldn't really be. So, I mean, the model makes kind of sense, but we might think that because we're very good on a training set, we might have overfit the training set. So, I mean, actually, I'm doing something very bad here because I evaluate multiple times on the test set. Never do that. Only evaluate in test set once. But so I see maybe I overfitted a training set. I set a regularization parameter to use a simpler model. Then I get slightly better. Now I have 88% correct. And now the features make a little bit more sense. And you see worst, waste, awful, boring, bad, terrible, dull, and so on. But I think they all make sense. Okay, questions about this? Enjoy is positive. No. Yeah. No, I didn't delete anything. So actually what I found was when I used a slightly different way to extract the words, what I found interesting is often people write in a text like 7 of 10 or 8 of 10, and that was indicative of positive reviews. And if they give 2 of 10, it's a negative review. Here I threw out these, or I separated them as 2 words, and so you can't find it anymore. But I thought that was kind of interesting. That's this function. Yeah, so I wrote it. The notebooks, everything I do is, I posted a link in the meetup group. So you can check this out later. Cool. Any other questions? Sorry? Out of vocabulary is ignored. I mean, it's just dropped, yeah. So if there's a new word, we just ignore it. So actually, I wanted to show you bigrams, but before we do that, I want to show you something else, which is awesome and called pipelines. So most of the workflows we have in machine learning are not someone gives you the perfect clean training data and the labels, and then you build a model and you're finished. Usually, there's like a lot of work you have to do before you can train your model. Like you need to do feature extraction, like we saw from the text, or you need to scale your data, or you want to select features, and so on. And so usually there's multiple processing steps before you can build your model. A mistake that many people do then is they start like playing with the data, cleaning it up, and scaling and whatsoever, and then they use cross-validation in building the model step. However, that's really a bad idea. The problem is if you use cross-validation on your last step, that means that all the previous steps already saw the test fold that will emulate your test set. So all the pre-processing steps saw all the data. If you get new data, which you will get once you go to production or go to a test set, the pre-processing steps will not have seen this new data, and so they will behave differently. The easy way around this is apply cross-validation to your whole pipeline. Whatever you do in validation, like the train test split, and cross-validation, always apply it to all the steps that are data dependent. And so there's a tool to do this in Scikit-learn, which is called the pipeline. So there's a function called makePipeline, and you can pass it any number of things that are transformers, so that have a transform function method. So like, for example, the count vectorizer and scaling of the data and feature selection, whatever you want. And then usually you have a final step that's like a classifier or a regression thing. And this thing is encapsulated in one object called pipe. Pipe, again, has fit and predict, as you might expect. And if you call fit, what happens is sort of illustrated down here. First, you take the initial data x that you put in, you fit the first transformer, say our count vectorizer, and then you transform the data. You get some different new data, x1. You use x1, give it to the second transformation, fit the second transformation, then apply the second transformation, get some x2. And then you use the last step, you call it just fit and fit to the final model. If you call predict on the pipeline, it'll just transform through all the way and then apply the classifier in the last step. Because this is like, basically, if you scale your data, you do something like this. This is just that this helps you to write shorter code, and you should use it all the time. If you're not using it, you're probably doing something wrong. Because either you're not scaling your data or you're scaling your data incorrectly. So yeah, really use pipelines. They have arbitrary many steps. The important thing is just that all steps but the last one need to have a transform method to create input for the next step. Yeah, okay. So this is how it looks like. Just make here, I have a standard scaler and a support vector machine. And now I can call fit and predict, and it'll scale the data and then make the prediction. Currently, it's tricky. You can name it class weights. No, actually, you can name it. Yeah, so there's a long-standing discussion on how to do this properly. It's not implemented yet. Maybe that's the best answer. You can make X anything you want. You need to wrap it and unwrap it again than in each. I mean, that's always, you can always do that, but it's probably ugly. Yeah, sorry. You can write your own pipeline, which is not that hard actually. Okay, so now I wanted to use this pipeline in this text example because we did exactly the same thing here. So here we had this count vectorizer to extract the vocabulary, and then we had the linear SVC to build the model. So I call make pipeline with count vectorizer linear SVC, and it'll give me one object that does both things at once. And so this is the code you need in Scikit-learn to do text classification. So that's kind of neat, I think. So what does this have to do with doing cross-validation over all steps? So now we have everything we want to do in one object, the text pipe. And so now we can use this one in the cross-val score function or in the grid search CV function. You can pass in this one thing. And then all the pre-processing steps will only see the training part of in the cross-validation and will test on the test part. So here I now do a search for the C in the linear SVC, so the regularization parameter. And I do this using this text pipe. So for each split of the data in the training test part, a new vocabulary will be built, and then this vocabulary will be applied to the test part. If you use grid search with pipelines, you might see here there's you need to adjust your parameter grid. So you need to tell the pipeline which step in the pipeline you want to adjust the parameters at. By default, the steps are named by using the class name. So here I want to adjust the C in the linear SVC. So I have to say linear SVC underscore underscore C. So it's class name double underscore parameter name. And this way the grid search knows what to do. Yeah, I think actually this takes so long. I think my laptop doesn't like me today. All right. While this is computing, I can show you how we can do n-grams. So here, I'm again making the same pipeline, but now I not only want to adjust the parameter C, I only want to see should I use 1 grams or unigrams and bigrams. There's this n-gram range parameter, the count vectorizer, that says the minimum and maximum number of tokens I consider. So the first parameter setting I tell it to try is minimum number of tokens 1, maximum number of tokens of 1. So just unigrams. The other parameter setting is minimum number of tokens is 1, maximum number of tokens is 2. So unigrams and bigrams. And wow, I'm gonna stop this one. Or maybe I'll show you later what the result is. But so, I mean, this now will build multiple vocabularies and so on. And so the cool thing here is that we can search over the parameters of both the pre-processing and the model at once. And so I'll let that run and show you in the end what the result is, because it runs for a little bit. Or maybe before I go on, any questions about pipelines or grid search with pipelines? No? Okay. Use pipelines. So I promised before that I wanted to show you some alternatives to grid search. So one of them that actually works really, really well is randomized parameter search. And it is as simple as it sounds. It is just pick random parameters. But there's sort of a trick to it. And this is like from a cool paper by Baxter and Bengio. It shows you how awesome it is to randomize. So usually if you do grid search, your parameters are continuous, but you specify a grid in which you want to search. So let's say you have 2 parameters. one on the x-axis and one on the y-axis. The one on the y-axis is really unimportant, doesn't matter so much on how well your model performs. The one on the x-axis is quite important. Now, in the grid search, we might tell our model, try 3 different parameters of the one on the x-axis, try 3 different parameters on the y-axis, because we don't know which parameters are important. Then we compute, we evaluate the model on this grid, and what we see is we see 3 different values of the unimportant parameter and 3 different values of the important parameter. And so the information we gained is basically only these 3 points. And so we missed the good parameter setting. If we look at a randomized layout for continuous parameters where we draw from a continuous distribution, it looks like this. So this is, again, 9 different evaluations, so it took the same time to run. But because of the randomization, we now tried 9 different parameter settings of the important parameter. So we got much better resolution on this important parameter, and we found the optimum. So this relies on your parameters being continuous and only some of them being important. If you have many parameters, usually only some of them are important. And then this works quite well. This is quite competitive with the best strategies there are, interestingly. And you don't have to define a step size. What you do have to define is distribution from which you want to sample the parameters. That's slightly tricky. Another cool thing is that you can start and stop this however you want. You can just always run it longer, and if you're satisfied, you can stop. With the grid search, if you stop it in the middle, you just have covered half the space. So that's not going to be any good. Also, in the random layout, if you add another parameter that's unimportant, it doesn't hurt. You can add all the parameters you want. It will basically not influence, it will not increase the runtime. So that's kind of sweet. So, okay, this is a too complicated example. But basically, instead of having a list, here I had a list for a C. I can give it a continuous distribution, and then it'll sample from this continuous distribution. And the class to do this is called Randomized Search CV. It works exactly like Grid Search CV, only in the parameter dict, you can give it continuous distributions. If you have integer parameters, you can just give it a list, and it'll sample from the list. Sampling from lists is not as great because it doesn't have the same benefit as sampling from these continuous distributions. Yeah. So they are awesome for continuous, but it's important to use continuous distributions for continuous variables, and for low-dimensional spaces, the grid search is usually faster. Questions about this? Yeah. Yeah. But that, yes. But that, I mean, but maybe there's more than one important parameter. And then you won't hit the combination. You don't know, basically you have 10 parameters, and let's say 2 of them are important, but you don't know which ones, but you still want to cover the combinations of these 2. Yes. Sorry, yes, but there's a better method. That is what I'm going to talk about next. Yes. you can skew the distribution. Actually, I don't remember exactly how I implemented that, but you can definitely adjust the distribution. You can also, I mean, you can give it a distribution object. So you can give it a distribution object that when sampled will give the, it's very simple to create your own distribution object. And that can be discrete. Yes. You can create any distribution object. It needs to have an, I think, RVS function. You need to give it an object with an RVS function, and it needs to give you a parameter value. So, and the better thing that we'll have soon is Gaussian process-based hyperparameter optimization, or more generally Bayesian optimization. So I don't know how much time I have, but so the idea here is another stolen picture. I should have put a picture of my student in there. Anyhow, so let's say there's some objective function, which is how well does your model do as a function of the parameter. So the x-axis here is the parameter you want to adjust. The y-axis here is the function you want, is the accuracy of your model that you might want to, wait, do we want to, that we might want to minimize. Sorry. We want to minimize here? Yeah, sorry, that we want to maximize. Yeah, so we want to maximize the accuracy of our model. And so the idea is there's this function that we don't know that says, given this parameter value, our model will be that good. Evaluating this function costs a lot of computation because it means building the model. What we can try to do is we can try to basically build a regression model that tries to predict how well will our model do as a function of the parameter. And we can use a Gaussian process to model this. So here you see sort of, we ran 2 experiments, this one and this one. And so we know how well the model does for these parameter setting. Now the question is, which next parameter should I try? And there are several heuristics. And one is expected improvement, so which trades off how high you think the function is and how much uncertainty you have. So here, for example, your upper confidence bound is pretty high, so you can say maybe it's pretty good here or here. You know that here it's not very likely to be good according to your model. So you try a parameter setting for which you think you might do well, and then you can refine your model, and you'll basically it'll keep in regions that are keep searching regions that are uncertain, but are expected to be high. And so this is sort of a smarter way to search, and it's not greedy because it has like some measure of uncertainty, and this works actually quite well. This will be implemented in the 0.18 version, so the next release of Scikit-learn. One of the main advantages of this over the randomized search is you don't need to specify ranges, or you don't need to specify priors of the parameters, so you don't need to specify distributions. You need to only specify upper and lower bounds, and then figure out the rest itself. So that's kind of cool. So where's the boss? How long should I do? No, I don't want to. Okay, if no one is here to tell me to stop, then that's your own fault. So another thing that I want to talk about, because it's like often forgotten, is scoring functions or evaluation metrics. So I talked about all this grid search and randomized search and Bayesian optimization for adjusting parameters. But the question is sort of, what is this metric we're trying to optimize? So far, I assumed it was accuracy. So by default, for classification, we use accuracy, so number of correctly classified points. And for regression, by default, we use R squared. But there's many cases where accuracy is a really bad measure, in particular in imbalanced classes. And I want to give an example of this. So here, I mean, I didn't show you this data set, but there's a data set of handwritten digits. There are digits from 0 to 9. It's not MNIST, it's much smaller. And so what I want to do is I want to classify, is a digit a 3 or something else? Before it was a balanced data set, and now I have 90% not 3 and 10% 3. And now I get a kernel SVM, and I run cross-validation, and it tells me it's 90% accurate. Is this a good model? No? Sure. It's random guessing. So the point is, so here I have a dynamic classifier that will always predict the most frequent class. So it's as good as random guessing, basically, or it's as good as predicting the most frequent class, according to accuracy. The point, though, it doesn't mean actually that's bad. It depends on what you want to evaluate. So usually, you have some preferences of do you care about precision, do you care about recall, and so on. But that's kind of tricky. So what we'd like to have is we'd often like to have a single number to summarize how good does the model do. And we want this, this number to work even if the classes are imbalanced. I think for imbalanced classes, accuracy is pretty broken, and it's not what we want. There's some other ones that we could try. So we can change the scoring metric by saying scoring. Will it work like this? So this actually tells me it's pretty bad. It tells me there was nothing was predicted as positive. So it actually did exactly the same thing as it always predicted. It's not a 3. So F1 is the geometric mean of, harmonic mean of precision and recall. And so that's usually better and more robust to if you have imbalanced classes. It's still sort of problematic, but because usually, like if you evaluate a classifier, you use predict, it gives you one result. This one result will give you a particular trade-off of precision and recall. So, but it might not be the trade-off between precision and recall that you want. Usually, depending on what your business goals are or what your research requires, maybe you care about recall, so catching all the positive cases, or maybe you care about precision, which means not catching any of the bad ones. So the thing that I usually like to use without committing to any of these precision recall trade-offs is I use the area under the ROC curve, which is this thing here. Let me make the lines a little bit bigger. So here what I did is I evaluated 3 classifiers. A support vector machine with 3 different values of gamma, which is like the kernel bandwidth. And so I can look at, I printed the accuracy. So the accuracy is 90% for all of them. So according to accuracy, they're all as good as random. What this plot shows here is for these 3 different classifiers, so blue, green, and red are 3 different classifiers. It shows the false positive rate against the true positive rate. True positive rate is the same as recall. False positive rate is how often you made a mistake, basically. If they increase the same amount, you're actually as good as guessing, which is the red classifier. Green classifier is a little bit better than guessing. The blue classifier, interestingly, is nearly perfect. So it goes all the way up to the left and then to the right, which is slightly surprising. So this has an AUC of 1, which is the best possible score. The accuracy is 90% though. Does anyone know what happened here? So the model, what AUC measures is whether the ranking of the points is correct. No. This is cross-validation. Wait, is it cross-validation? No, it's not cross-validation, sorry. What happened here, AUC, it's more or less a ranking loss. It measures whether, how often you were more confident for a negative sample than for a positive sample. And what this tells us here is we ranked them all correct. So it gave all the things that are actually 3 a higher score on being a 3 than all the non-3s. So it ordered them all in the right way. However, it put the threshold on the wrong at the wrong point. It put the threshold so that it said nothing is a 3. If you change the threshold on making a decision, it will have got everything right. And so I think that's kind of interesting. And so usually I try to use AUC for building a model. And then afterwards, I try to find a threshold to get the precision recall trade-off that I want. Yeah. So anyhow, that is me saying don't use accuracy. Use what is more useful for your case. There's a list of predefined scorers that you can find here in the documentation, like F1 score or precision or recall or average precision is also good. Yeah. And you can pick any of these and you can just say, as I did here, scoring equal to something like, if I do scoring equal to rock AUC, it will use area under the curve and tell me this model is actually perfect, apart from the threshold. Yeah? Yes. Yeah, actually I want to read up on that, so I don't know. Yeah. I think that's the best. So I don't know. I mean, you could average the curves, but I'm not sure what the right way to interpolate them or to average them is. And yeah, if you know a good paper about this, let me know. Okay. Any other questions? Okay. I think I'm a bit over time, but I wanted to tell you what the cool new stuff is. So give me a sec. So 0.17 is the current version. It's been out for like, I forgot. I think early this year. The cool things that we have is latent Dirichlet allocation with online variational inference. This is to build cool topic models. It was slightly faster than GenSim. Then GenSim took our Cython code. Now we're at the same speed again. That we have a new solver for logistic regression and rich regression, which is called SAG, and that's faster than liblinear in many cases. Let's see, is it actually? In some cases. So, and it's very precise, and it scales great to large data sets. We have a new solver for non-negative matrix factorization, which is like, I don't know, factor of 10 faster than the one that we had before. This one is now using coordinate descent. Before we had non-negative least squares, I think. We have t-SNE. I don't know, who knows t-SNE? No? Learn about t-SNE. It makes pretty pictures to impress your boss or your reviewer. So, okay, if you don't know t-SNE, but I'm going to explain this plot. So I have this data set of these handwritten digits that are really small, you can barely see. And so there's here, this uses the classes 1, 2, 3, 4, 5. Now we did a dimensionality reduction to 2 dimensions of this data set, not giving it any class information. So this is sort of nonlinear PCA down to 2 dimensions. This is the outcome. Now the model does not know anything about the classes. We colored them by the classes. You notice something? So I think this is amazing. So basically, it completely separated all the classes. Well, there's apparently two kinds of ones. The one with the tick and the one without. But basically, this model, completely in an unsupervised way, separated out all the different classes. So it's mostly good for visualization, but it's really cool for visualization. And we have a new solver for that that's now, I don't know, 50 times faster than the one that we had before. No, that's not interesting. That's not interesting. Oh, maybe that's. If you like to do bagging of models, we now have a voting classifier that allows you to put a bunch of models together and average their results. Also, so 0.18 will come out in the summer and we'll have awesome, cool stuff. The Gaussian processes were completely rewritten and are much more awesome now and much more powerful. We have some neural networks, though we don't use GPUs, so they're semi-useful. We have improved cross-validation. The interface is slightly nicer. We got rid of the randomized PCA class, and now PCA magically decides what kind of methods to use. So here, blue is the last release, red is the current release, and you can see that sometimes it got like twice as fast, which is nice. Oh, and also in the summer, I'm gonna come out with this book. If you want to learn more about Scikit-learn, buy my book. There's a hellbender on the front. Sure. Okay, thanks. Questions? So, okay, the question is, I have trained a tree model, I have a new point, I want to find out where it maps. And yes, you can do that. You can keep all the points fixed and add a new point. That's not, so that was not implemented properly in the pull request, and so I removed it before I merged it, and we need to re-implement it, and it's not done yet. So if you want to contribute, that would be awesome. I think that's a really cool feature. And it's possible, but it's not implemented. Okay, so I guess two-part question. Do we want DAGs instead of pipelines? And yeah. So the thing is, okay, so the way I like, maybe. So currently it is done that there's a single input. Actually, I like there to be a single input. There's currently something that's called the feature union, which allows you to do a Y and then go together. So you can already get, yeah, but it is actually, the feature union is a split and a join. And then you can put pipelines in the parts. And so you can build relatively complex graphs, but there's a single input. And then you can, let's say, select certain rows. Usually that's what you want to do. You want to select some features and operate on them, and then do something else on some other features, and you can do that. So question was, can you, for pipeline, can you have batch and online options? Currently it's only batch. We're thinking about how best to implement online, because if you have ideas for how to do the online, the thing is you can't do it streaming because some of the operations need to iterate over the data once. So let's say you want to scale it between minimum and maximum, you have to go over data once to find the minimum and maximum, then you have to go over it again to pass it through to the next step. And so we need to find the right interface to do that. But I want to do that, but it's not done, not solved. More beers? Pizza? Yeah? Thanks.